everyone. In the last video, we have seen what are random experiment, sample space, and event. Sample space is nothing but the universal set for a particular random experiment. So, here it is convenient to use set theory for event also. So, few properties from set theory we will see how it is useful for computing probability. Okay. So now we will see what are the mutually exclusive events, mutually exhaustive events, and how to calculate probability. So in this, we will see two approaches: classical approach of probability and axiomatic approach of probability. Uh, so first, we will see how this set theory properties can be used for events. Suppose A and B are the two events for random experiment with sample space S. Then first we will see A intersection B. So this is the sign of intersection. And this is the Venn diagram. So here this is the S whole set with sample space, and this is A event A, and this is the B event. So these common elements are nothing but the A intersection B. So here I can write collection of all elements, collection of all outcomes, because I'm telling about the event, so I can write outcomes that are elements of both event A and B, right? So suppose A intersection B for any events, there is no element between them. Then we can say A and B are mutually exclusive event. Now we will see what is A union B. So A union B is nothing but the occurrence of either A. So here I will write down the name of events. Suppose this is A, this is B, and this is the sample space. Then uh, A union B is nothing but the occurrence of A and occurrence of B, right? Or occurrence of A and B both. So here I can write down what is A union B is the collection of all outcomes that are elements of either event A or B or both, right? So suppose A union B is equal to sample space. then we can say A and B are mutually exhaustive events. This is the sample space, and suppose this is the event A and this is the event B. Then here A intersection B is, here I will write A intersection B is equal to 5. So no element between A and B, and A union B is whole sample space, right? So here A and B are both mutually exclusive and mutually exhaustive. So here I can say, so third I will write the partition of events. So suppose A and B are two events such that A intersection B is equal to phi, A union B is equal to sample space, then this A and B are form a partition of sample space. So this partition of event is useful while studying the conditional probability. Then I will explain it again. Now we will see classical approach of probability. Classical approach of probability is probability of an event is equal to number of favorable outcomes of an event A. So here we are calculating probability of A, then it is number of favorable outcomes divided by number of favorable outcomes in sample space. In notation, I can write P of A is equal to N of A. So number of elements in event A divided by number of elements in sample space. So here we can take one example. Suppose the random experiment is a tossing a coin. Then what is the probability that A is equal to, so I can denote A by getting a head. So here I need to write down the what element will come under A. So under A I will get only head, right? And the sample space there are two elements, head and tail both. So here n of A is 1. So probability of A is equal to n of A. So here I will write n of A is equal to 1 and n of S is equal to 2. So this is very simple example, but this you can apply all other problems also. So this is 1 by 2. So probability of getting ahead is equal to 1 by 2, right? But for this classical approach, there are assumptions like most important assumption is equally likely outcomes. What is mean by equally likely outcomes? Equally likely outcomes is nothing but the all outcomes are having equal probabilities. But if you will see any real life situation, then it is not possible that consider all events are having all outcomes are having same probability. For example, you can take one approach that suppose you want to find out the probability that the newborn baby is a female. So, according to this rule, equally likely outcomes, probability, because here there are only two outcomes, male or female. According to this assumption, probability of newborn baby is a female will be 50%, right? Or zero point 0.5. There are lot of things on which this probability is depend. Like this probability changes region to region, right? In India, suppose we are having the females less female than male, but in out of India, that can be a different. So it is depend on the regions, and all other factors can be there. So on the basis of that, this probability will change. So this equally likely outcome is not possible for every real life situation. So as we seen, this classical approach method is having some limitations. Finally, this Kolmogorov founded the axiomatic method of defining probabilities. He proceeds with the study of properties of probabilities. These properties of probability founded on the set of axioms. So axioms are nothing but the properties of probability. So now we will see what are the properties of probability. So first property of probability is non-negative property of probability. For any event, A, probability of A is greater than or equal to 0. So this is the non-negative property. Then second property is probability of sample space is always 1. Third, probability of A union B is equal to probability of A plus probability of B when A and B are mutually exclusive event. So this property, third property, is known as additive property. So these properties are nothing but the axiomatic approach of probability. We will see this example. A bag contains 9 balls, of which 4 are red, 3 are blue, and 2 are yellow. The balls are similar in shape and size. The probability of drawing a ball any ball is equally likely. So here we can use classical approach. So here what they have given the next. A ball is drawn at a random from the bag. Calculate the probability that it will be a red. So here we will write down the sample space first. So sample space contains 9 balls, 4 are red, 3 are blue, and 2 are yellow, right? So here n of s is 9. Now next, here I need to define my event. A is the event that a ball drawn at random is red. So how many red balls are there? There are 4 reds. So I can write n is equal n of A, that is favorable outcome of A, are 4, right? So my probability of A is equal to 4 by 9. Next, similarly here I can define B, a ball drawn at random is yellow. So here n of B, because there are 2 yellow balls, so here I can write 2. So probability of B is equal to 2 by 9. Similarly, blue, so I will define event C as a ball drawn at a random is a blue. So here n of C is equal to 3 blue ball. So my probability of C is equal to 3 by 9, that is 1 by 3. Now next fourth example is not blue. So this is nothing but the complement of C, right? So probability of C dash means complement of C is equal to 1 minus probability of C. Then 1 minus 1 by 3. So this is 2 by 3. So my probability of not getting a blue ball is 2 by 3. Then fifth one is either red or blue. Now we will see fifth example, either red or blue. So red I have defined by A and blue I have defined by C. So probability of A or C. So probability of A or C means probability of A union B. So here probability of A intersection B is 0 because there are no elements in common. So these are the two disjoint event. So I can write probability of A union B is uh, probability of A union C is equal to probability of A plus probability of B. So probability of A is 4 by 9 and probability of C is 3 by 9. which is equal to 7 by 9.